My name is Stefan Luding. I will give Elasticity Theory in Module 6 and for pre-masters, and it will be about linear elasticity and material mechanics. Now, today we do the introduction. At the end of the course, I will do an introduction and everything what you are not feeling comfortable with now, everything what you today have not understood in this next 10 minutes or 15 minutes, that one should be clear in the introduction then after the course. So I will give you a wider overview, some things you cannot really get now because it's new, completely new, but after the course you should be able to understand everything what I tell now. So that's also giving you an idea what we are talking about and what we will be talking about. Now, Module 6. And for the pre-masters, you zoom into elasticity, your conditions are slightly different. In Module 6, it's about materials and in particular about polymers. It will be about elasticity and mechanics. That is my part of the course. You will talk with me about this. And it's about tribology and contacts, mechanical contacts between different materials and the mechanics thereof. And in the Module 6, the project combines all this. So I will make reference sometimes to the project, so the pre-master students are or are not informed, maybe not even informed about this. But anyway, the project is supposed for the Module 6 students to bring all these things together. For the Module 6 students, there is something which was mentioned in the project description, and that is about mechanical, static, and impact loads. Okay, so mechanical statics and elasticity, statics, solid materials, and as elasticity, that is what belongs together. And impact is when elasticity reaches its limits. And that one I will teach in relation to materials and material mechanics. What are the limits of elasticity? But most of the time, 70% of the course will be about elasticity, and then materials, mechanics will be about the limits of elasticity. Now, Elasticity Theory overview, and this is common to both groups of the students. Today, introduction. This is what I'm doing now. And the sequence in the whole lecture series will be from mathematical and mechanical basis, ability to perform and interpret finite element, and the knowledge about material behavior. Now, in the introduction, I reverse the order. Later, most of the course will be about mathematics and mechanics. It will be rather theoretical, about linear algebra, tensors, stress and strain. That comes later. Also, after my lecture, one of my student assistants will show you, actually not student assistant, postdoc assistant, sorry, Kia, will show you how to perform and interpret finite element. This is not goal of this course, but we want to show you this as an example because this is what you will be doing in your future career, most likely, if you ever work with mechanics or solid mechanics or elasticity theory. Okay, and knowledge about material behavior I will show you now first. So first, number 1, 2, and 3, but the majority of the course will be 3, 2, 1 later. Now, materials. Overview over materials. And this is about fluids and solids in general. So you have water and you have sand where you can walk on. Sand is solid-like almost, and fluid you can swim in, but you cannot walk in. Most of us cannot walk on water. Now, fluid materials like water or gas is also a non-solid. Solid materials, that is metals or polymers in particular, a lot of reference will be made to polymers. It's also composite materials like concrete or fibrous composites. It's organics, about wood or tissue or bone. That are all solid materials. Now, we also have another type of solid materials which are granular, like the sand on the beach. So sand, soil, rock, grain, rice. They consist of solids, but they are cut into many pieces, particles, powders, pills, granules. And they are also very small particles, but they are also very big particles, like the sun, our Earth. These are big particles circulating around each other. Okay, and there are many applications like additive manufacturing or geotechnical applications or natural disasters like avalanches. So all these things have to do with materials, their behavior or their not so good behavior, and that they become fluid or solid. And an avalanche or a landslide, the land is solid, then it becomes an avalanche fluid, and then it becomes solid again. What you see here top right is a silo. This is a train, so this is 4 meters. This monstrous silo is 50 meters high, and actually you see that it fails. So the material in the silo is static, and then it does something to the silo structure. The silo structure fails, and then everything is flowing, and then we have a problem. Okay, so this is general considerations about materials. We are actually working with all these types of materials, in particulate materials, particle systems. And this is an example which most of you might maybe still remember. Before the time of mobile phones, we had an hourglass in order to know how long our eggs would be cooking on the stove. Okay, and in this small hourglass, particles are flowing. And in this hourglass, particles are also starting to flow when we open. Now, open. No, actually, they were flowing already. Okay, show it again. Okay, these particles are flowing also, but then they block. And during this blockage, this could cause so much forces or loads on the outside walls that this silo breaks. In some situations that can happen. Okay, that was related to the moving before. So we have materials which are fluid, we have materials which are solid, and particle systems are sometimes fluid, sometimes solid, sometimes both, like in these flowing situations. Okay, and we call fluid to solid transition jamming, and we call the solid to fluid transition unjamming. This is a general wording. Now, when we talk about linear or nonlinear materials, there are more things to say about. In a fluid, the kinetic energy is most of the time important. The viscosity is important. In a solid, the potential energy, the mechanical energy is important. And sometimes if both, then both of them are important. In the transition from fluid to solid, we talk about phase transitions in general. I will not talk about phase transitions in this course very much, but I wanted to give you the general picture. Okay, and phase transitions, you know, when you melt ice, then you become a fluid water. That's a phase transition. When you have fluid water and you freeze it, now we will have winter freezing, then you will see phase transitions of melting and freezing. Now, this I stole from Wikipedia. And this type of plots and more information you can see on the Wikipedia links. I will give you the material details later. So nonlinear material, sometimes solid, sometimes plastic. This is about stress on the vertical axis, force per area. I will come back to that one many times. And strain on the horizontal axis. Okay, strain is change of length. Stress is force per area. And the red line is increasing the load on this simple bar. So the load on the bar is tensile forces. We stretch the bar, and the area of the bar, A, is just signifying the area. Force per area is then stress. Now at the beginning, in regime 1, we have elasticity. So stress strain has a linear slope. That's linear elasticity, and E is the modulus. Okay, at point 2, it becomes nonlinear. At point 3, it becomes plastic. At point 4, when we get up to here, the bar is already damaged. And when we go back, we will go back to a strain of 0.2% permanent deformation. So it can be that we go back on an elastic line, but there is a permanent plastic deformation. Okay, now this was explaining this figure. I will give you much more details about stress, strain, and it will get quite more complicated and more mathematical. But this is one of the things in the axiom you must know to interpret and to understand such graphs. The nonlinear material behavior. In metals, for example, a stress-strain curve can look like this. The red curve, you go up linear to a limit, and then you have a wiggle, you have a maximum, it goes down, it weakens, and then it fails at 0.3. Okay, so there are names for this. I don't want to bother you with all these names. You can read it in Wikipedia, and we will come back to the details of the explanations later. But in the exam, you must be able to understand this plot and give names to 0.2. Understand what is 0.3. Understand what is 4 and 5. What's the difference? Okay, so this is in order to tell you what you don't know yet. Most of you probably don't know. Some of you might know. Okay, nonlinear material, sometimes fluid. Shear stress. Shear stress and shear strain rate. Afschuwsnelheid in Dutch, Schaufspanning in Dutch, shear stress in English, shear strain rate in English. Okay, now when we talk about a fluid, then we plot stress versus strain rate. In the previous plots, it was strain on the horizontal axis, now it's strain rate. If you have a Newtonian fluid, then you get a constant slope again, but the horizontal axis is different, so the meaning of the slope is different. In the previous plot, it was a modulus. In this plot, in a fluid, it's a viscosity. And then you can have shear thinning fluids or shear thickening fluids. These are all words which I will come back. Shear stress, shear strain, rate of shear strain, and there are different types of fluids, shear thinning, Newtonian, shear thickening, as in the left plot, but there are also yield stress fluid like Bingham plastic, which have a finite shear stress at zero shear rate. Okay, and our particle systems, which I showed you some pictures and examples before, they are falling into this class. Everything what is linear relates to linear, but most of the materials will be nonlinear at some point. Okay, so linear materials, nonlinear materials. Most of the time I will talk linear. Sometimes I will talk nonlinear. Okay, now next part of the overview concerns rheology. Seems somebody is waiting in the lobby. Can you please let them in?
He is in.
Okay, good. Thanks. I'll go back to PowerPoint. Yes. So it's about the general rheology. Again, I stole it from Wikipedia. And this is about continuum mechanics in general. That is the mechanical and mathematical art of understanding materials. And then continuum mechanics is split up in solid mechanics and fluid mechanics. I was talking about the word solid and fluid many times. So most of the time we will talk about solid mechanics in this course, and most of the time we will talk about elasticity. In fluid mechanics, you had some courses on fluid mechanics, and Newtonian fluids or gases are described by continuum mechanical equations. Solids are described by continuum mechanical equations, but the equations, some terms disappear in one material and they are important in the other material, or other way around. So the elasticity and the Newtonian fluids, they all are described by the same continuum mechanics, but the equations look different because some terms are off in one case and not in the other. Okay, and when it goes from solids to fluids, there are many solids which behave plastically, which is not linear elasticity, which is halfway towards fluid. Non-Newtonian fluids are halfway towards solids. And this area zone here, this is the domain of rheology, where elastic solids are not perfectly elastic anymore. Rheology becomes important. When Newtonian fluids are becoming nonlinear or non-Newtonian, rheology is the science which we are talking about. Okay, but our focus will be on elasticity in most part of this course. In the last section, I will do a lot about materials more. Okay, now, what are the goals of the elasticity course? It's about linear, small deformations, such that we stay elastic and linear. Isotropic means it will be direction-independent materials. Wood or bones are direction-dependent materials. Fibers are making direction-dependence. We consider simple materials like homogeneous polymers or metals where the direction is not important. In this course, in many future courses and many applications, you will need anisotropy. Okay, now the goals I mentioned already. It's about understanding mathematical and mechanical basis of all this. It's about linear algebra, tensors, stress, and strain. Okay, and that will be 60–70% of the course talking about this. It is about the ability to perform and interpret finite element. I mean, you will not learn in my course to perform finite element, but you will then be able to interpret these things. And it's about knowledge on material behavior. Now, the canvas side, the elasticity theory material on the canvas side, what have we provided for you? Some of you have probably already scrolled through the material. They are on Canvas. You should all be able to see them now. There are a schedule on elasticity. Those of you who clicked on the link have been there, evidently. The presentations and materials. There are readers and books. There are videos, and there are assignments and solutions. So that are the 5 slides. I want to give you a few more details on that. So the schedule, when I refer to sections, I want to refer to this numbering. On the today, first is introduction. Later I will do some mathematics and repeat your high school mathematics. Number 2 is about scalars, vectors, and tensors. That are definitions which you will need later. But the major part is stress. That will cost me quite some hours. And then strain, and then material behavior brings stress and strain together, and also brings up energy. And then finally, different materials, the limits of elasticity or beyond elasticity, and that is then materials and material theory. Okay, and this will be presentations. So the presentations will take you, if you attend all of them, about 10 hours, maybe a little bit longer. But however...
We have a question. Do we need to have specific literature for this course?
Yes, exactly. Thanks for the question. I'm just answering. I try to answer it. Now, the presentations, the material is online already. The practice material is online already, and that is the biggest part which I recommend that you spend your time with. I have a big amount of hours on practice because the exam will consist of mathematical operations with pen and paper, which you have to do. And if you don't practice, you will not pass the exam. Most of you will not pass the exam if you do not sufficiently practice. So we provide you practice material, we provide you example exams from previous years, such that you get a clear idea what is expected during the exam, and the exam will not change too much from that what you see on Canvas. And most of you, many of you, probably don't need anything else. Okay, the online links, like the Wikipedia links, which I mentioned to you today, those of you not those of you, those links, you should spend a few hours with to read through them. It's not the major part of this course, but some questions in the exam will be about those online links. Okay, so think of 2 hours, maybe a little bit more, such that you get an overview of that, what I just mentioned, rheology, solid and fluid continuum theory, stress-strain relations, plastic, elastic, material behavior. Those words must be clear to you. What is isotropic, anisotropic? What is homogeneous, inhomogeneous? These definitions must be clear, and that will be asked in the exam. Okay, so the colorful part is that what I consider as absolutely necessary to pass the exam, to understand and reach the goals of this course. Now, the books are additional reading material. If you do not understand some of my lectures, maybe you want to take a look in one of the books. There are also readers. All these are not 100% aligned with my course, and they are also not absolutely necessary. Many of you will be sufficiently prepared when you understand my presentations, get the practice material, do self-study practice at home, and read a little bit of the online links, and that's it. Okay, so I hope that answers the question. You can have a book, and this book, the set book, for example, or the ready book, if you buy it on paper, I think it costs you something. The PDF should be free to download. This book, if you now use it, it will accompany you probably for the rest of your life. So it's not bad to have the book, but you don't need it absolutely, I think. Some of you might need, some of you might not like how I explain things. Then a book is an alternative, but it's not absolutely necessary, I think. Okay, and then we have a page with videos. So we will place the lectures there. And there are also some some World Wide Web links already to YouTube or Vimeo, where you can see videos by other lecturers. Again, if you don't like my lecture, maybe some other lecturer gives you a better introduction and overview to that, what I want to teach you. Okay, some of them are quite professional and good. I have selected those which I liked and those which are not going too far beyond that what I want to transfer in this lecture. Clearly, there's always more, but I try to restrict myself. Okay, so videos, lectures, World Wide Web. And then we have assignments and solutions for practice. Okay, practice comes back to the beginning. So there's a page with all the assignments solutions again. So I recommend try the practice material without looking at the solutions. But if you get stuck and if you do not really understand, the details of the solutions are given there. We also will do quizzes to complement this. Okay, I'm almost done with the introduction. Next slide. Yes. Now, elasticity theory. This was about the goals. And next, after 2-3 minutes, short break. Maybe there are some questions. Next, I will ask Kia on the floor to present you a quick example of a finite element program, how someone in research or in industry would work with a simple finite element program problem and how that looks like. And again, there will be some words which you will be hearing, which you do not yet know. Okay, those words after the course, you will understand them better, much better. Okay, and afterwards I will continue with the mathematical and mechanical basis. So today, in this introduction, as I said, I gave you a very basic knowledge and overview on material behavior. This is done now. You will see finite element in a few minutes after a small look at the chat and if there are questions. And then we will do mathematical mechanics and basis for the rest of the day, for the rest of the slot.